So let me introduce the last speaker of today.
If there is a knotted Rabe orbit, and there exists infinitely many orbits. And the proof is very easy. I can sketch it very quickly. So, because it's dynamically convex, you know that you have this open book decomposition. So you have this surface of section which is bounded by one Rabe orbit, right? Because there's a surface of section on the disk, then as was discussed, you get the second Rabe orbit. So you have this P1 and P2. But they're both unknotted because they both bound disks, right? So as soon as you have a knotted Rabe orbit, that means you have to have a third one. And once you have three, you have infinitely many by the two or infinitely many thing. So it's, I mean, there it's almost trivial corollary. But it's pretty interesting, I think. What else? So there's a paper by, say, Vandenberg, Van der Verst, and Robert Greist. So I think this is in Inventiones 2003. So here they study a certain class of fourth order Lagrangian systems. And here, so it turns out their configuration space is like, so what they end up looking, they view these things as they have this, so the configuration space is two-dimensional and they have this time axis, and they look at one periodic, just like loops in this space, and they have this action functional, which the critical points of which are closed orbits, and they look at the gradient, the flow of this thing, which is not always globally defined, but anyway, but at least it's defined well enough that you have some kind of a flow. So they look at something like, you might have a three periodic orbit, which might look something like, and has these things might link with each other somehow. So you get these braids in the configuration space, and then they look at classes, homotopy classes of loops that sort of have a certain linking structure with respect to that braid. And they develop a sort of Conley index for this. Whose, if it's non-trivial, then they show that there exists an orbit in that braid class. And using this idea, they can prove things like the existence of infinitely many Rabe orbits. Not Rabe, sorry, it's a Lagrangian system, but they can prove things like infinitely many type orbits or even exponential growth of orbits. And recently, with work with another author, they're extending it to do, so they do a Floer homology for disk maps, which again uses the structure of they have some braid with it has to have certain properties, and they look at certain homotopy classes of loops on the complement of that braid, and they develop either, in this case a Conley index, in this case a Floer theory, whose non-triviality implies existence of other orbits. It's fairly interesting. And here the answer they get actually depends only on the braid class and on what they call a proper braid class, which is just the homotopy class of this braid on the complement of the chosen fixed braid that they select beforehand. And then finally, there's sort of similar, but in a different setting. There's a paper by Angenon, where he studies curve shortening. So I think this is in Annals, maybe 2006, I'm not quite certain. And here what he does, he studies flat knot types relative to certain closed GD6. So he supposes that you know that there are certain closed GD6 in a surface. And then he studies knots that have a certain kind of intersection type with those already known GD6. So you have certain fixed ones. Maybe I should draw this with color. So you have these fixed geodesics, and you study the space of curves that have a certain like intersection pattern with those geodesics, and you apply curve shortening and see what happens. And he's able to prove, he develops a Conley index theory and is able to show that if it's non-trivial, that there has to be some geodesic in that what he calls a flat knot type or flat knot type class. So, and as an application, he takes S2, and I think with any metric, and takes a closed, simple geodesic, and he considers the inverse rotation number. If this is not equal to 1, then he's able to prove that you get an infinite number of PQ type satellite geodesics, which just means that they sort of wrap around Q times while wiggling back and forth P times. That's roughly what that means. And these PQ numbers are related to this rotation number. It's like there's the rotation number. As fractions. They occur between 1 and the rotation number, whatever it happens to be. I won't write that out. So what we do. So I'm going to try and do something like similar, but rather in the context of Rabe dynamics. And we'll see a little bit. So here, it only depends on the knot type. Here we see like that it depends on some kind of rotation number, some index. So, I mean, we'll see that this is generally the case, but I'll try to remark why sometimes this can also be hoped to be true, that it's only depends on the homotopy class and not the rotation numbers as well. But usually it depends on the rotation numbers. Okay. So the tool we're using is to try to define contact homology and the complement of these Rabe orbits. So the main problem will be, so if you have this link L, then you look at M minus L. So M is a compact thing, but when you take this link away, it's no longer compact. So in particular, the compactness results so the compactness theory doesn't apply, at least immediately. So one has to find a way to figure out what's going on, and really, like it's actually, I mean, there are times when, I mean, really, it's a problem. It's not like, it's not something artificial. So that's the main problem to overcome, to get compactness in the right way. So, okay. So now I'm going to sort of review notions from contact geometry, contact homology. Probably you've heard this a few times already, but I think I have to say this thing, so I'll try not to belabor the point too much. If you get really bored and you want to think of something, you can maybe try to think about how to solve this problem. And let me give a hint at least. The hint is you have this. So the main problem is sort of that you might start to break one of the. I mean, there are other things, but those are fairly easily solved. The problem is you might have like a component of the link, and you might end up breaking at one of these orbits. So the question is, suppose this is elliptic. Why can't this happen? So it turns out it can't happen. That question is why. I mean, if you consider cylinders that don't intersect it initially, okay, that's the problem we really have to solve in the end. So, but okay, so let me just keep going. So we start with now with a 3-manifold with a coriated contact structure and a contact form on it. So here, 3 is very important. As we saw in all these cases, here we're in 3 dimensions. Here we're in 2 dimensions, but I mean, it's 2 dimensions, but sort of almost 3. Well, okay, so you just ignore that. And here we're also in 3 dimensions. So 3 dimensions seems to be sort of important. It's absolutely crucial for the tools we use. As we use intersection theory of holomorphic curves. That will be very important. Okay, so we have now the Rabe vector field, which I'll denote by R. which seems to be the letter we've been using mostly in this conference. So remember, it's just defined by these two properties. And we get a flow RFT. And I'll denote by P the set of closed orbits for this flow, so closed Rabe orbits. And let me remark that this includes multiple coverings. So in contact homology, when you actually consider multiple covers of Rabe orbits, not just the simple orbit, and that causes problems sometimes. Well, but you sort of have to include them. Okay, and then we have, so these guys basically generates the chain complex. So maybe I'll just call it C star. It depends on the contact form, of course. Modulo some complications, which we can avoid. We'll just ignore. And it's graded by the Conley-Zander index, which has been maybe not described but used very often in this conference, so I won't belabor that. There's something I want to say. For us, the parity of the Conley-Zander index will be important. In dimension 3, the parity can be described by dynamical, by the dynamics of the linearized flow. So let me say what that is. So if the orbit is elliptic, then this is odd. If it's negative hyperbolic, so it just means hyperbolic, but it switches leaves of the stable and unstable manifolds, so it just like rotates it again, then it's also odd. And if it's positive hyperbolic, then it's actually even. So when you iterate these guys, it alternates between odd and even, odd and even. If this was always odd, like I would be able to use these too, but because of this alternation, it's a little bit difficult. And we shouldn't be, maybe it's not clear why, it's not clear to me, like just from the dynamical behavior, why this parity is important, but rather from the asymptotic operator. There's a strong relation with the asymptotics, which we'll see later. Okay. And so we would call the differential so the differential, it counts rigid, in a particular sense, cylinders in the symplectization. So let's recall, symplectization is just a manifold which is homeomorphic with R times M. And when you write with these coordinates, you can write I used A. You can write the symplectic form like that, where A is, I'm almost always going to use A to denote this coordinate, and pretty often I'll use U to denote this M coordinate. So what's the almost complex structure? So this has been discussed before, so I'll be brief. So on the contact planes in M, so we have the contact structure, we consider the set of these guys, so d lambda compatible, almost complex structures. And then we extend it to the symplectization by setting, so J, so it'll send this vertical R direction, which is, I'll denote like that, sends it to the Rabe vector field at that point. We're calling that R. And then that J of R is minus d by dA. Right? That extends entirely to to the tangent space. And then remember, we study holomorphic curves. So our maps from punctured Riemann surfaces. So let me call this capital U, or let's use U twiddle. I think this has been used before, so it's simpler. So with coordinates AU, and we study the PDE, which is, you can write it in conformal, so choose conformal coordinates, S plus IT. You can write it like this. And then plus the energy condition, which this energy condition is equivalent to force asking that it be asymptotic at punctures to ray orbits, at least. So I should also say that I need to assume that this flow is non-degenerate in the sense that all closed orbits have non-degenerate. When you look at the eigenvalues of the Poincare return map, they're never equal 1. And then that forces asymptotic behavior automatically by deep theorems of Hofer, Wysotsky, Zender. Okay, so, and these things collect nicely into moduli spaces. Well, ideally anyway. Well, okay, first let me give an example. So there's this important example, especially for what I'll be doing are trivial cylinders, which are also a very simple example. So suppose we have a Rabe orbit, say x of t. A closed Rabe orbit, so just x naught equals r. This satisfies the ODE. X of 0 equals x of t. Okay, so then we get a holomorphic curve for free by, so let's just think of this as a map on a circle, or yeah. So we get a map U, so I'll define the coordinates. So A of st I'll let be t times s, and I'll let U of st just be x of t times t. Let me just extend this periodically to r, and this will be defined on r mod z. So this is defined on r times s1, so we get a cylinder. And it's very easy to check that this satisfies the holomorphic curve equation because of the way we chose it, that it has this nice splitting part. So like the projection onto the contact structure of this thing will be 0, so it satisfies the PDE. And then over here, just in the s direction, we just get, the vertical thing, and in the t direction, we just get the ray direction. So you see, it's satisfying the PDE. And it turns out it's easy to check that as finite energy. Of course, it has the ray asymptotics. So these are important for two reasons. One, they provide the sort of the right asymptotic model, and second, we're going to use them in a very non-trivial way. So let me review the properties that I'll need, many of which have probably been discussed already earlier on. So the first, most important thing is the asymptotics, which say that at punctures, holomorphic finite energy curves, so I'll just say J holomorphic curves, but I always mean finite energy. J holomorphic curves are asymptotic to a trivial cylinder. And in fact, in the non-degenerate case, we can say exponentially. And this will actually be very important, and there's a very nice asymptotic description. Which is all given in this paper, H. Wysotsky Zender. Has the word asymptotics in it. And I should also point out that this has been sort of refined by work of Seifring in the case where you have rather than just a trivial cylinder, we have two curves that are asymptotic to the same Rabe orbit, but maybe not trivial. He describes the sort of relative asymptotic behavior of one with the other. And for intersection theory, this is very important. So this is also, yeah, I'd like to note that. The second component we need is a compactness theorem. So Bourgeois, Eschberg, Hofer, Wasatsky, Zender, 2003 in GAFA. And this says, this was discussed by Umberto and Pedro and others already. So I won't go too much into detail until I really need something from it. And I'll say what I need from it. Or rather, I shouldn't say compactness, I should say compactification. The third component is the Fredholm theory. So that in nice cases, we get manifolds or orbifolds or polyfolds, maybe eventually. Yeah. So roughly speaking, they come in finite dimensional families, but the full story of getting all the transversality right is quite difficult, and there are a lot of people working on it. However, for the purposes we need, we can prove transversality in lots of cases. So in interesting cases anyway. Oh yeah, and the last ingredient we need is positivity of intersections. So it turns out that holomorphic curves always intersect positively, and if the intersection is transverse, it's not difficult to see that this is the case. The problem is though when the intersections points occur at a singularity. So if two curves intersect and they both have a singularity at the intersection point, it's difficult to do the analysis. It's actually quite hard. So this was done by in the case of pseudo-holomorphic curves and symplectic manifolds. It's done by McDuff and Mikhailov and White. So locally, but I should also put in here the work of Richard Seifring, where he does sort of an asymptotic intersection number. He finds some sort of asymptotic intersection number when two curves are asymptotic to the same orbit that has nice counting properties and it also still has positivity. So I mean, I should draw a picture to point out why this work is not obvious, why you need to consider something like this. So you might have two curves and they might intersect like that and be sort of asymptotic to the same thing. But then these two intersections might sneak off to infinity, right? They might just ride up in as you vary in the moduli space. They might just go and disappear at infinity. So the question is, how do you see these things? And it turns out this escape or whatever is captured by winding numbers. So a relative winding number of the two holomorphic curves in infinity. Which is controlled by the asymptotic orbit operator at the orbit, which is controlled by the dynamics of the orbit, and that's why these things become important. Okay. So, was there anything else I wanted to say about that? Oh yeah, so I should say a little something about the differential. So, okay. So let me just write down a sort of simplified version of the formula of the differential. So if you have an Rave orbit gamma, which represents a generator in the chain complex, then we define the differential to be the sum over things that look like this. So I mean, I'll just draw it pictorially. So you have some sort of holomorphic curve in the symplectization. So we have some negative asymptotic orbit delta, and we count only the rigid ones. So which in particular means in this case that we look at ones with Fredholm index 1. Fredholm index coincides with the expected or virtual dimension of the moduli space. And the reason we have 1 is, remember from von Kurt's talk, that we have this free R action, so we have to mod out by that. So we get sort of an extra thing that we kind of don't want. So then we have to assign some sign in a complicated way. And also, this is not really 1, this is some integer. It depends on some things, but it's okay. Nothing terribly. But it's roughly something like that. And then we have the theorem. Well, so all this is introduced by, I should say, Leshberg-Hofer, Giventhal, so in the SFT paper. So in there, they sketch the proofs of, so theorem, so this is e.g., this is from that paper, but there's still, I should point out that there's still some analysis that's still kind of yet to appear, so, and various people are working on this. So first thing is that d squared equals 0, and the second thing is that the homology well, I should first say if the chain complex is 0 in degree to where, remember, in dimension, so in general, the grading is given by the Conley-Zender index plus n minus 3. So for us, this is Conley-Zender index minus 1. And so their theorem is that the homology is first d squared equals 0 if this happens, and then if also, so the homology is independent of the contact form if in these degrees. So in particular, it's an invariant of the contact structure. Okay. So now I can say what I did. Okay. So now okay. So now let me take this 3-manifold M with its contact form, and suppose now I have a link L which is composed of a finite union of orbits, closed Rabe orbit. So closed Rabe orbits, but with the further property that the gamma and gamma is elliptic. So each component, I assume each component of the link is an elliptic Rabe orbit. Okay? Okay, so now we try to do cylindrical contact homology on M minus L. And so we can prove the following. The theorem. So, okay. Suppose there are no, we have to know something else first. Contractible Rabe orbits, closed Rabe orbits in M minus L. So by contractible, I mean contractible in M minus L. Not just in M, but like So as long as one of these orbits intersects any disk, that caps them off should be okay. Then cylindrical contact homology of, so this is M minus L with the form lambda restricted to there. So this chain complex exists, I mean, d squared equals 0, and the homology only depends on, so let's say the asymptotic Alexander index indices of the components of the orbit of the link. So by asymptotic Alexander index, I really just mean the following. So I define the asymptotic Alexander index of an orbit to be the limit as n goes to infinity of the Alexander index of the nth. So I cover this by map of degree n, and just divide by n, just take this limit. So it turns out this number is all, for elliptic orbits, this number is well defined, and if it's non-degenerate, we get some irrational number. Yeah, so it depends on this sort of, and this, remember the Alexander index, some sort of measure of the rotation number. This thing is sort of just gives a more precise idea of what the rotation number is than just the first iterate. If you consider all the iterates, which this number basically tells you the Alexander index of all the iterates of, or all the coverings of that orbit. Okay, so it depends on these numbers. So let me sketch now, finally, the proof of why this should hold. So, idea of proof. Yeah. Yeah. So if I fix, so what I mean by the homology only depends on the asymptotic Alexander indices means like if I, so let me have my manifold M and I have this link L which is now fixed. So if I consider the set of all contact forms for which those are all elliptic Rabe orbits, and I fix the rotation numbers on each Rabe orbit, then it depends on, then it's invariant of that. Like it only depends on those rotation numbers. So you consider the class of forms that have those as Rabe orbits with those rotation numbers. And it depends, well, then this number only depends on the rotation numbers, not the particular form. So I'll sketch the idea of the proof. And actually, it only depends on L up to, I also mentioned, it's not too difficult to show that it only depends on L up to the link up to transverse isotopy, because you can, if the link lies somewhere else and it's, you have some other link which is transversely isotopic to that, you can just find a path of contactomorphisms which push the first link onto the second, and then they lie over one another, and then, just pull back the contact form. It should be okay. But anyway. Okay, so the idea of the proof. So what we do is we look at moduli spaces of cylinders which do not, so lying in M minus L with image and asymptotic orbit. All in M minus L. So yeah, I can just say it that way. Better to say it that way. So in particular, so if I view them as living in M, these cylinders so when I think of them as in M, they don't intersect the trivial cylinders over the orbits in L. So let me just set for notation this to be just the union over the components of L of the trivial cylinders over that orbit. I just use Z, this just denotes the trivial cylinder over that orbit. Okay. So what I want to do is show compactness of these moduli spaces. So compactness. So it turns out that one can indeed prove some compactness. So let's recall the proof that D squared, well, let's just consider special cases. So when we're considering the proof that D squared equals 0, well, what are we doing? We're considering the boundary of the modulus space of cylinders with index 2. So these are sort of like one parameter families modulo the R action. So if we can prove D squared equals 0 if the boundary consists only of these things. So we want to show that the boundary consists only of these configurations. And here, since we're in M minus L, we need, so these are, it's broken in orbits x, y, and z, and none of x, y, and z are not components, or do not live in, none of them are lying inside the link L. Otherwise, that would be bad, right? Because, oh yeah, sorry, I should say that. I mean, yeah, so this chain complex is generated by the Rabe orbits, which are not in L, right? Because I threw them away from the space, right? So I can't break at an orbit in L. If this was in L, then it would be bad. It wouldn't have compactness. Also, I'm counting cylinders here, which have intersection number with the trivial cylinders over L is equal to 0. So in an appropriate sense. Okay. So the easy part is the following. So you need that to be the case for both cylinders. So let's take one parameter family of these guys, and that doesn't intersect this. It doesn't intersect this orbit L. And suppose it breaks into two orbits, which is fine. But suppose that one of these orbits intersected this trivial cylinder ZL in the end, right? Well, this would be bad because, well, we have positive intersections. So this intersection is sort of, I mean, it's stable under homotopies. If you push this curve around, it's got to persist because there's some local intersection number that's positive, right? So what would happen is, well, just before it broke, we'd find that there had to be an intersection with that trivial cylinder also, because you have sort of C infinity low convergence of these things. So the existence of some local positive intersection implies that you had to intersect before, and this would be bad. This just couldn't happen. Because conversely, if you started with some good configuration which didn't intersect, as soon as you glue, you have something that doesn't intersect. And along the way, an intersection can't just pop up because of positivity of intersections. Okay? So this configuration can happen. So it just remains to see why, well, what else is there? The other bad thing that could happen is you could have a pair of pants bubble off. So you have this family of cylinders, and then we get some sort of bubbling. like this. For example, this is possible. So, but I kind of cheated in the hypotheses by supposing that, making this hypothesis, there are no contractible Rayborn orbits in M minus L. So, I mean, this disk here, when I project it down to M, it's going to, since this is not contractible at M minus L, it has to intersect the orbit L, and therefore this thing has to be intersecting the trivial cylinder over L. Because there's this intersection downstairs, so when I lift upstairs, there has to be an intersection. Right? So because of that hypothesis, this can't happen either. So the last terrible thing that could happen is the following. So we might have this sequence of cylinders, but it might break at some orbit gamma, which is inside this link. So this is what we have to exclude. So this is the question I asked before, why can't that happen? So the answer comes from the asymptotic description of holomorphic curves. So the asymptotic formula it assigns, sort of a rough way of saying this, it assigns a winding number to holomorphic curves. So this is also particular to dimension 3. It assigns a winding number to holomorphic curves at their asymptotics, like asymptotically. So an asymptotic winding number to holomorphic curves. So I think Pedro mentioned this in his talk already, right? And this is related to the asymptotic operator. Asymptotic operator. And remember, the asymptotic operator you can think of as something representing the Hessian of the action functional. So it's some symmetric operator with certain properties. I'll maybe say a little bit more about this in a second. So what happens is for the asymptotic formula is so at an elliptic orbit, or rather at any orbit with odd Conley-Zender index. So again, this is in dimension 3. The winding numbers associated to curves positively and respectively negatively asymptotic to that orbit. So they all differ. By which I just mean that there's So by this I just mean if you have a holomorphic curve and it's asymptotic some orbit, then from above, so then there's some winding number equal to, I don't know, let's say k, right? And then you have some curve approaching it from below. It has some winding number, but a priori this has to be different, and in fact has to be smaller. So k minus some positive number, positive integer. Okay? And this is a contradiction because what happens is, you have this, so this thing is not supposed to intersect the trivial cylinder, and neither is that by positive intersections. And we start off with a family that didn't intersect. But what happens is, just over here, this holomorphic cylinder is winding around some number of times. And over here, this holomorphic cylinder is winding around some other number of times. Right? So just before just before this breaking happens, you're going to have some curve here around which, so this curve will be winding around some number of times, and then maybe some long time later, it stays in that neighborhood of that orbit for a long time, but then some time afterwards, you'll have some different winding number. So in particular, during that time, it had to cross through that orbit, and that introduces an intersection. So we have an intersection with that thing we were considering, and that's a contradiction. So this can't happen. And that's the reason why this can't happen. Okay, so that explains why d squared equals 0. And just a brief word as to proving why this thing only depends on the rotation numbers. So then one tries to mimic this argument but now in a non-R invariant case. So for invariance. So when you're proving that contact homology only depends on the structure, not the form, or all this sort of stuff, what you generally do is you take the symplectization, which is like R times M, and you consider almost complex structures. So you have some contact form at plus infinity and some other one at minus infinity. And you consider the set of almost complex structures which agree with the symplectization almost complex structure in a neighborhood of plus infinity, and another one that agrees with is adapted to this form of minus infinity. And you have a nice symplectic structure in between, so you just sort of find some J which agrees with these guys, plus and minus infinity. And I want to do some sort of, but you don't have the notion of a trivial cylinder anymore, right? Because it's sort of not. Yeah, you just need odd, right? But the problem is, you could. What if this was a cover of something, right? Like if it was a multiple cover, then if I had an odd hyperbolic orbit at a multiple cover, it might be even, and then these winding numbers might actually agree for that. So you could break at an even cover, and it's not so happy. So yeah, it's a little bit of a problem. Maybe it can be sort of circumvented because you're already supposed to be throwing those orbits away or something, but I don't know. Okay, so yeah, part of the problem is I don't have these holomorphic or trivial cylinders. So what I do is I consider, I have these orbits, gamma subset of L, and I just look at R times that orbit, and I consider the set of almost complex structures which actually make this thing holomorphic. And this is okay. You should always be able to do this. So the problem is when these rotation numbers differ. So suppose this had some asymptotic Conley-Zender index which was smaller. So say it's theta, and here it's like theta plus epsilon. So these are the asymptotic Conley-Zender indices. So when you take a very high covering of this orbit, this thing will have some negative index. And so the intersection theory of Richard Seifring says that if this index is very negative, then it should have a negative self-intersection number. And this leads to, so you kind of introduce some negative intersections. I mean, not honestly, because the holomorphic curves can intersect negatively, but they can have negative self-intersection. And this problem actually ends up wiping things out. And you can see this without even thinking about negative self-intersections, because what happens is the winding number you get over here, so it has to be bigger than the one you get just below, but then the index goes up. So then this thing might be higher, and then you drop down, but you might end up higher again. So the winding number here could be the same as the winding number there. So you can't get that linking argument that I said over here. However, if they have the exact same growth of Conley-Zender indices, then you can't ever, this doesn't happen. They have sort of the same thing. So you don't run into problems that way. But it's a rough idea of why that works. Okay, so I think, is there anything else I want to say? I think that's roughly it. Okay, so thank you.
Is there any question?
Some contact homology on of Rabe orbits. Yeah. So I haven't yet got around to that finished doing that part. But you can see a lot of, like, you can take the sort of simplest thing you can do is take the type 3 sphere and sort of study that, and you can really get a feel for what the computations are there. Also, one should be able to compute, like I think in many cases it's been studied for open book decompositions, which is sort of ideal for this sort of thing because the binding is elliptic and all the orbits have to link around, all the closed orbits have to link with that, with the binding. And there have been some computations there, like where they actually find what the orbits are in the holomorphic curves, so it should be possible to read off from something like that. So you think there are cases where it should be possible to read off what the answer is. But I haven't written any down just yet.
More questions? Okay, so let's thank Al again.